welcome everyone. We're going to take a look at using Yarp, which is a reverse proxy, and customizing it to handle multiple Kubernetes clusters and more, but you're going to have to wait and see what that more is. What you won't have to wait for is the takeaway from the talk. Now, Yarp is a reverse proxy toolkit. It's built in C#, and it expects that you're going to extend or rewrite components of the implementation. And so it makes that an easy process to do. Standard reverse proxy functionality that you'd expect from Nginx or HA proxy is available for you, and you only need to extend the parts that you require for your use case. So there's a lot of great content that's available already for setting up Yarp as a standard load balancer, but I really want to highlight how easily it can be customized when you have a need that arises. So we'll set the stage with the scenario that was causing us problems with the off-the-shelf solutions. We'll look at the standard Kubernetes load balancing and why it fell short, and then see how we designed a system using Yarp to enable our multi-cluster load balancing. And finally, we'll see how we were able to utilize this beyond Kubernetes. So my name is Ryan. I am a software architect at Blizzard Entertainment, and the team that I work on mostly builds internal tooling for support, localization, game integrations, as well as external services like the player support site and self-service options. I actually recently hit 20 years at Blizzard, and that gets you a helm, which I think is pretty cool. Additionally, for about 19 of those 20 years, I've worked with the same team, and it turns out that gets you something as well, which is a vast catalog of systems that you need to continue operating and maintaining as the business evolves. And so that was our driving challenge that we had. And we really want to standardize as much as possible everything that we do to lower the burden on our team to maintain all of these systems. And these are varied systems in what they do and in when they have load. Some are during the workday in the United States. Some of them are used around the world. Some of them are used in times when players are online. And so we standardized our hosting for these services using Kubernetes, and specifically using a small number of clusters that host all of the systems on them, as opposed to having separate systems, separate clusters for each system. This reduces the operational work. It also prevents the clusters from specializing for each specific system, thus increasing the complexity of trying to manage them. In addition, we run redundant clusters. That means that a workload is going to run on multiple 2 or more clusters at any time in an active-active setup. And this allows us to run upgrades or other maintenance operations without needing to find a off-peak time, which is difficult with the varied systems that we run. And so we can take down a cluster and do an upgrade while we still have active clusters that are servicing traffic. This greatly reduces the risk and allows us to update more frequently, which also means we have smaller updates that get made, which further decreases the risk. And we also, as a standard procedure, do our upgrades by tearing down a cluster and recreating a new one, which also exercises the ability for us to do that should the need arise, because that is our standard operating procedure. So we get benefits from those multiple clusters, but there are also some challenges that introduces. And the one we're going to look at today is multi-cluster load balancing, or getting clients to these workloads across multiple clusters that can be created or destroyed at any time. So multi-cluster load balancing isn't a common scenario right now, and it certainly wasn't very common in 2020 when we started our journey of looking for a solution to this. If we look at standard Kubernetes load balancing, Uh, you will have your cluster that's running pods. These are your workloads that you want requests to ultimately get to. And in a public cloud, there are managed offerings for creating a load balancer that will allow requests to come in. And the general pattern is that they will run a pool of layer 7 proxies, which are able to look at HTTP requests, find out the host name, the path, headers, other things about the request itself, and determine which service it should go to, and then pick one of the workloads to send the request to. And the cloud will run multiple instances of that layer 7 proxy for availability and to allow it to handle higher scale if needed. So then the layer 4 proxy or routing will expose a single IP address that clients are able to contact, and it will forward to one of those layer 7 proxies, which looks at the request and forwards it onto the workload. Now, that layer 7 proxy needs to know how to look at a request and determine what service to route it to. And that configuration gets pulled by a Kubernetes controller, which is just a process that runs usually in the cluster. And it's going to look at various resources in the cluster, like service resources, ingress, gateway, as well as others that we don't have time to get into. But ultimately, it's looking for what services should be exposed and what workloads are providing that service. And the controller, when it sees changes in that, will create configuration that gets applied to the layer 7 proxy. And this is available in essentially every Kubernetes cluster in some form, but it does assume that there's a single Kubernetes cluster that is being used to create that configuration for the proxy. And in our case, we want to have this work with multiple Kubernetes clusters that we're running. So if we imagine what we would like to happen is we have these multiple Kubernetes clusters that are each running the same workloads. So a service gets deployed, it runs pods in both of the clusters, and they're going to be running their controllers to discover these services and pods that are running. And we want to somehow combine these portions of configuration from each cluster into a single config that we can then apply to the layer 7 proxy. And then the proxy is able to route to the backend in either of the clusters that we've shown here, since both of them run workloads for that service. And a solution like this doesn't exactly exist. And so we were looking at options that were available. I'm going to squish down the diagram here just to save some space. This is the same picture. We've got multiple clusters that are running, and we want that configuration to somehow get merged. Now, I will mention there are some multi-cluster service ingress and gateway options that do exist, and we have tried using them, but for various reasons, they weren't applicable for us. One of them is that most of them are specific to one public cloud, and we do run across multiple clouds. And so that runs against our desire for a standardization, which would require that we have separate solutions for different clouds. Also, some of the clouds we run in don't have multi-cluster options. A second reason is that many of those multi-cluster options are only working with external load balancers. The majority of the services that we expose are internal. And so that also meant that it wasn't an ideal solution for us to use those existing solutions. And so we were trying options, and eventually around 2022, we heard about this product called Yarp, which is the reverse proxy toolkit. And we were eventually able to come up with a solution that follows a very similar pattern and uses a discovery controller that we wrote and uses Yarp that we run and manage as our layer 7 proxy into our clusters. And we haven't got time to look at the C# discovery controller, But if you are interested, the Yarp repository does have an implementation of a Kubernetes controller that provides ingress, and you can see what resources need to get watched, how to use the .NET Kubernetes API client in order to watch those resources. So you can check that out to see what that portion of it entails. The reason we don't use that controller is because it as well assumes that it's working with one cluster that's configuring the Yarp proxies. And so what we needed was a way to get these multiple config pieces and somehow get them merged together into the proxy. And so we use an intermediary of object storage, which is available in any of the public clouds as a place to store these config portions. And then in Yarp, we need to collect all of those and merge them together before we apply them to the proxy. And so in order to handle writing the config without overwriting, we use this layout and object storage. A gateway is a naming we use for a pool of Yarp proxies. In this instance, Gateway US are our internal facing services in the US region. Gateway External US are our external facing services, and they each have their own pool of Yarp proxies that expose them. The second segment is the source, which in this case is the Kubernetes cluster, and then the service name, and it ultimately stores JSON that is used to define the routing and the set of backends that a specific cluster has for that service. And so this allows us to have cluster 1 and cluster 2 write their own config portions without overwriting each other. And you can imagine if cluster 3 is spun up, it's going to discover and write out to cluster 3 in object storage. So this allows us to write our config in a way that each cluster has its own separate portion. For then the merge process, what we logically want to happen is the Yarp proxy is configured for one specific gateway, and it will pull all of the objects that start with that gateway name. So the gateway US is going to pull those first two objects. It's going to ignore the source because it doesn't care where it's from. It just needs to get the information. And then it's going to get the distinct services across all of those. So in this case, just service A. And then it will aggregate all of the backend pods or the backend workloads from all of the different sources. So if cluster 1 has 2 pods running, cluster 2 has 3 pods running, it will create a single collection of all 5 of those pods as the backend workloads. So logically, that's what we want to do, but we still need to get Yarp to do that logic that we want. So if we look at how Yarp is integrated, it is a NuGet package that integrates into the standard ASP.NET Core pipeline. And this has benefits because you can utilize the policies for rate limiting and cores and auth in your Yarp routes. And you also get distributed tracing out of the box because the rest requests come in through a standard ASP.NET Core pipeline and they get forwarded as HTTP client calls, which is already instrumented. And then Yarp itself integrates in as an endpoint routing registration, and it has its own pipeline, which we see coming off to the right here, with various components that implement the standard behavior of reverse proxies. But each of these is designed to be able to be removed, replaced with your own implementation, or even to have you add and extend your own entries into this pipeline. So we're going to look today at how we've customized the configuration portion. But in addition to this, we also have our own implementations for health checks, for request transforms, and session affinity to fill other needs that we have with our proxies. Also, since mapping the reverse proxy just registers in the standard endpoint routing, you can still have controllers and razor pages and minimal APIs that are registered alongside in the proxy to add even more functionality, such as showing the config that a specific proxy is using, along with backends and their health status on the proxy itself to help with visibility into what's going on. Now, with these components being available with standard implementations, we have the C# available for what's being implemented. And so if you want to see what the functionality is, you have the code available and you can look and see how it's been implemented. And the code is always the best documentation. So for actually setting this up, there's very little that needs to gets put into place. As I mentioned, Yarp is available as a NuGet package. So we add the reference to that in the web application builder. We set up the reverse proxy dependencies in the service collection with the add reverse proxy. And then at the second arrow is where we map that reverse proxy into the endpoint routing so that it's able to handle requests that match its routing config. And then the last piece we have is the configuration. And if we look at the commented line here, that's how typically Yarp is configured. And this is going to pull from the .NET configuration system, which is your app settings.json or wherever else it is you're pulling your configuration from. And that's typical for a static or a manually created config. That would be similar to creating a configuration for an Nginx or an HA proxy. But in our case, we have our own custom logic where we want to pull from object storage and do this merge operation before it gets applied. So we have our own object storage config provider that implements the iProxy config provider interface, and we register that with dependency injection, and Yarp will use that to create its config when it needs it. And so I mentioned that we have the code for the standard implementations, which can be a great starting point to how you write your own behavior. And in this case, there is an iMemory config provider that Yarp ships with, and it provides the iProxy config provider interface, which has a get config method. This is what Yarp will use to get a snapshot of the configuration, as well as a change token that can be used to signal updates. Then the in-memory config provider adds an update method where you can call it with a new set of configuration. It will apply that internally to the provider and trigger the change token that will get Yarp to pull a new snapshot of the config, and it will have that available for the next request that comes through. So we use this and we copy pasted the in-memory config provider for our object storage based one. We made the update private, and then we started a task that runs in a loop that periodically pulls the config portions from object storage. It runs the merge operation and then calls update to let Yarp know that there's new config that's available. And we're actually not going to look into that code because it's in the end pretty uninteresting. It uses .NET clients to pull from object storage that all of the cloud providers have. It does a distinct to get the services that are available and a select many to get the destinations. And that simplicity of the logic is kind of the point here. We've seen very little code to add our own implementation. And the logic that we want to run is also relatively easy to express in C# code. And because Yarp was set up to allow customization easily, this is a very straightforward process for a .NET developer to see. So if we look at how this lifecycle works, if we deploy a new service to a cluster, the deployment system is going to create the pods and for the workloads and create a service with the annotations that describe how the routing should be configured. And our discovery controller monitors those resources. And as they change, it will write out config for that cluster and that service. And all of those clusters will do the same. At this point, the discovery portion's done. And then Yarp is going to periodically pull those object storage objects and merge them together. If the configuration is different from what's currently applied, then it will call update, which will trigger Yarp to pull that new configuration and start using that. And so at this point, we've now done no manual work, and our new service is available for routing through the Yarp proxies. And as those pods get created and deleted through the normal Kubernetes life cycles, then it will update Yarp with the new backends and the new services that are there. And then finally, we had used object storage as a way to simplify and reduce complexity in the implementation. The Yarp proxy itself doesn't need to know about Kubernetes, and the Kubernetes discovery component doesn't need to know how to update the Yarp proxies. They just have a shared location where that config is written. And that ended up being very beneficial for us as we looked at some of our services that are not running in Kubernetes. So we had services that exposed APIs and web pages before we were using Kubernetes. And those are running on Linux containers that were just VMs that we managed, as well as .NET Framework services on shared IaaS hosts. And we were able to add manual config in Yarp to allow those to be proxied through a standard Yarp interface, which gave us good distributed tracing and allowed us to remove other infrastructure that was running HA proxy and going through hardware load balancers that we had, which did not have the same visibility that we get using Yarp. We eventually moved the Linux containers into Kubernetes hosting, so those went away. And for our .NET Framework services that still existed, we ran those. We run those now on auto-scaling VMs that have Docker installed, running as Windows containers. With them being auto-scaling, we can't use a manual config anymore. We have to have something dynamic. And what we did there is we wrote a self-discovery component that runs inside each of those Windows container processes. And when they start up, they discover themselves and they write out a config portion of just that one services on that one machine. So the target's the VM and the service is the name of the container that's running. And with that in place, Yarp just does what it was doing before, and it pulls in the config portions, merges them together, and it's now exposing our .NET Framework services. And as the VMs scale up and down, those routes and backends will update on the Yarp proxy, and our services are now available through the same framework with the same observability with a very standard C# .NET process that the entire team is familiar with operating and maintaining. And so, again, the specific implementation of our use case isn't the point of this. The point is that Yarp is designed to be easily customized for use cases where the off-the-shelf reverse proxies don't fill the need. It's a common language and framework for C# developers to customize and to operate. And if you can write the code, then Yarp can do it. So I've included the link here to the GitHub repository for Yarp, where all the code is available, as well as the NuGet package for incorporating this into your systems. And I hope this has inspired you to consider Yarp when you need a customized or a consistent proxy to get your job done. Well, thank you so much for coming out.